Hi everyone, welcome to Step 6 of the MEDomicsLab testing phase. In this step, we transition from the design layer to explore the development layer, unveiling the much-anticipated learning module. The objective of this step is to create a machine learning model that can deliver robust results on our data. To achieve this, we'll be crafting two scenes. The first one aims to compare the performance of machine learning models based on patients' timelines. We want to investigate whether a model performs better with data from all time points, as our assumption suggests. The second scene will delve into the comparison of model performance based on selected variables. We will construct this scene based on the insights gained from the first scene, determining which time points are most instrumental in achieving optimal performance. At the beginning of this step, you should have a time point folder with at least a learning and a holdout folder, each containing 4 CSV files. In this step, we will exclusively use the data from the learning folder, which is the output of Step 4, while the holdout folder will be utilized in the next step. Let's start by creating the first scene. Click on the learning icon. A section for creating a new scene should appear on the sidebar. Click the Create Scene button, enter scene_1 as the scene name, and then press Create. Now, if you open your Experiments folder, a new folder named Scene_1 has been created. It contains an empty model folder, an empty notebook folder, and a .medml file. Double-click on the .medml file to open the scene. Click on the top left button to display the list of available nodes. Let's focus on creating a simple pipeline for now. Every pipeline must start with a dataset node, so let's drag a dataset node into the scene. You have two options in this node: the MEDomicsLab standard format or a custom data file. Here, we'll stick with the default option, which is the MEDomicsLab standard format. Click on the node to select the files you want to use as a dataset for your pipeline. The node will automatically detect which files match the MEDomicsLab standard format in your workspace. As this process can take a few seconds, you may encounter the message that no files have been found. Simply wait and click on the node again to select your files. For this first pipeline, we are going to select only the T1_learning_modified CSV file. Then, in the tag section, we are going to select all the tags, and in the variable section, we are going to select all the variables. Then in the target section, we are going to select the target column. In this initial scene, we are aiming to compare the model performance over time, so we are not making tag or variable selections at this stage. Let's also rename our dataset node to T1. To do this, click on the node name, which is Dataset by default, enter the new name, and press the Tab button on your keyboard. Now, let's drag and drop the Compare Models node into the scene. Connect it to the Dataset node. This node will train all the available models from the PyCaret library, which forms the foundation of our learning module on our dataset. It will return, as output, the model with the best accuracy. To complete this pipeline, we are going to add an Analyze node at the end. Connect it to the Compare Models node. By default, the Analyze node plots the AUC curve of the model passed in parameters. Here, as for some models in PyCaret, the AUC is not available, and as we don't know yet which model will result from the Compare Models box, we are going to display another plot. To proceed, click on the Analyze node. Set the plot option to on to make it appear on the node. Press Save and enter Feature in the Plot Box option. This will allow displaying a feature importance plot. Now, we have our simple pipeline ready to execute. Press the Run button at the bottom right of the scene and wait for the experiment to execute. This can take a few minutes. You can track the progress of the process using the progress bar displayed at the bottom of the screen. Once the results have been generated, a success message will appear, and you will be able to click on the See Results button at the top left of the scene. This will open a panel at the bottom of the scene, displaying the results by pipelines and by nodes. If you click on the T1 node, you will be able to see the parameters that PyCaret has set using the dataset for the experiment. You will also have access to the original dataset you passed to the node. Then, if you click on the Compare Models node, This will display a few metrics about the model's performance in the experiment. The displayed models are sorted by accuracy by default, and the first model from the list will be the one used in the following nodes. Now, if you click on the Analyze node, you will see the feature importance plot for the best model from the Compare Models node. If you're executing the steps simultaneously with the video, you may have noticed that you have different results from mine. Don't worry, this is normal, and we are going to explain why. Let's explain what PyCaret does while we create a simple pipeline like this one. At the beginning of a machine learning pipeline, you initialize your data using PyCaret setup function, corresponding to the dataset and clean nodes in our learning module. The setup function requires a dataset and the name of the target column. PyCaret then initializes elements for the pipeline. First, PyCaret divides your dataset into two parts, the training set and the test set. The training data is employed to train and optimize your machine learning model, while the test data is reserved for evaluating the created model. You can pass your test data as a parameter to PyCaret. However, this option is not yet implemented in our application. If you don't pass your test data to PyCaret, it will utilize the scikit-learn train test split function. This function performs random sampling on your dataset before splitting it into training and testing sets. The random sampling step is executed with the aid of a random seed, and each split is linked to a specific seed. By default, PyCaret randomly assigns a seed at the start of each pipeline execution. To ensure the replication of the same experiment with a consistent split, you can set this parameter in PyCaret using the session_id parameter in the dataset node. This ensures that your test and train data will remain consistent across all executions. Then PyCaret will define folds on the train data to use for the cross-validation part, which will be executed using the train model or compare models nodes. The definition of the folds will also be done using a random seed, also defined through the session ID parameter of PyCaret. By default, PyCaret uses the stratified kfold method from scikit-learn to define the folds. The stratified method ensures that each class from the target is represented equally across each fold. Let's return to scene 1. Now that we have a better understanding of what PyCaret does with a simple pipeline, let's enhance our initial pipeline by adding some parameters. Click on the T1 node, and then click on the plus button. We are going to enable two options, index and session_id. As we've seen earlier, the session_id parameter will allow us to replicate the same splits for the test data, train data, and folds for the cross-validation part. In fact, if we run the experiment multiple times without changing any parameters, we will consistently obtain the same results. The index parameter will allow us to specify that our identifiers column is an index. Otherwise, this column will be considered as a feature column and may be used in the prediction. Click on Save. Then we are going to set the session_id as 123, which is a number I choose randomly, and set index to subject_id. Next, let's enable two options on the Compare Models node. Firstly, we prefer to consider models with the best AUC as the best models. By enabling the sort parameter, we can specify this criterion. Additionally, the Compare Models node can return a list of the best models. This way, the Analyze node will evaluate all the models from the return list. To achieve this, we'll enable the in_select parameter to return more than one model and compare the best models among them. Now, set AUC as the sort option, and 2 for the in_select option. If you are uncertain about which option corresponds to what or which parameters you can set, please note that we've implemented tooltips from the PyCaret documentation to assist you in understanding the possible options. Now, since we specified that we wanted to sort models by AUC, we are confident that the returned models will have the AUC plot available. Therefore, we can set the Analyze plot parameter to AUC. Let's execute the experiment. After generating your results, open the result panel. If you click on the T1 node and expand the parameter accordion, you will observe that the session ID parameter has been set as specified. Additionally, you will notice that the shape of the original data frame now includes 38 columns instead of 39 from the previous execution. This is due to the index parameter, where the subject ID column is not considered when training the model. Now, if you click on the Compare Models node, you can notice that the list of models is sorted by AUC, as expected. And if you click on Analyze, you will see two AUC plots, which represent the resulting AUC of the two best models from the previous node applied to the testing data. However, it's noticeable that the results are not very good. Let's take a moment to examine what these AUC plots are displaying and why there are 4 curves on each plot. You can click on each plot to view them more clearly. Firstly, the plots come from the Yellowbrick Python package, which extends the scikit-learn API to make model selection and hyperparameter tuning easier. Under the hood, it's using Matplotlib. An AUC plot allows the user to visualize the trade-off between the classifier's sensitivity and specificity. The AUC is the area under the ROC, Receiver Operating Characteristic, curve. The curve displays the true positive rate on the y-axis and the false positive rate on the x-axis, both on a global average and per class basis. Here, the plot displays the ROC curve for the class 0 and the ROC curve for the class 1. Given that we only have 2 classes, the per-class curves appear quite similar. However, in scenarios with more classes, the per-class curves are computed using the 1 versus rest method. This involves calculating scores with the considered class as the positive one and treating all other classes as the negative one. The microaverage curve is calculated by summing up all the true positives and false positives across all classes. The macroaverage curve takes the average of curves across all classes. The AUC associated with each curve is displayed in the legend. Let's return to our scene. Click the Results Mode Off button to deactivate the results mode. We are going to create another pipeline that incorporates the data from time points T1 and T2. Drag and drop another dataset node into the scene. As before, rename the node by clicking on its name. Name it T1T2 and press the Tab key on your keyboard. Next, choose the T1_learning_modified and T2_learning_modified files in the File section. Select all the tags and all the variables. Verify that the target column is configured as target. Now, we are going to configure the session ID and index parameters as we did in the T1 node. Click on the plus button and enable these 2 options. Enter subject_ID in the index field and 123 in the session ID field. Finally, connect this node to the Compare Models node and run the experiment. Open the Results panel. As we now have 2 pipelines, you can observe that the results are displayed by pipelines. In fact, you can compare the performance of the models from the 2 pipelines simultaneously by clicking on the nodes and deploying the pipeline results. Indeed, since the only thing that changes in the 2 pipelines is the dataset, we are comparing the performance of the models based on the data we acquired through our previously defined time points. When you click on the Compare Models node, you may notice that the results from the T1-T2 dataset do not appear to be better than the ones in the T1 dataset. As before, you can check that your dataset parameters have been set as you specified. Here, you may notice that as we have data from T1 and T2, the number of columns is greater than in the first pipeline. Finally, when you click on the Analyze node, you can see that the curves for the second pipeline, which correspond to the evaluation of the model on the test set, appear to be better than the ones in the first pipeline, with an AUC of 0.63 for the best model. Let's exit the results mode and add other pipelines to our scene. Add a dataset node to the scene. Rename it to T1, T2, T3 and press Tab on your keyboard. Select the CSV files associated with these 3 time points. Choose all the tags and all the variables. Verify that the target column is set to target. As before, add the index and session ID options. Set subject_ID as the index and 123 as the session ID. Finally, connect this node to the Compare Models node. Let's do the same with all the time points. Add a dataset node to the scene. Rename it to T1, E2, T3, T4 and press Tab on your keyboard. Select the CSV files associated with these 4 time points. Choose all the tags and all the variables. Verify that the target column is set to target. Add the index and session ID options. Set subject_ID as the index and 123 as the session ID. Finally, connect this node to the Compare Models node. Run the experiment. Let's compare the results of our pipelines. Open the result panel. If you look at the results from the Compare Models nodes, you can see that the best models AUC scores are similar for the T1, T2, and T1, T2, T3 datasets. However, the score for the T1, T2, T3, T4 dataset is better with 0.68 for the best model. Also, we can note that the extra trees classifier is the best model considering AUC for the 2 last pipelines, and the second best model for the first pipeline. Now, if you observe the analyzed plots, you can notice that the best models from the 2 last pipelines seem to perform better than the first pipelines on the test set. With an AUC of 0.70 for the T1, T2, T3 dataset and 0.73 for the T1, T2, T3, T4 dataset. Also, by visualizing these plots from the 2 last pipelines, we can note that both extra trees and random forests seem to work better than the other models. As the cross-validation scores given by the Compare Models results are very similar for the T1, T2, and T1, T2, T3 datasets, we will work with the T1, T2 dataset for the second scene. This choice aligns with a real-life scenario where predicting a patient's death as early as possible is crucial. In this first scene, we suspect that the models struggle to train due to the large number of columns compared to the number of rows. We believe that better results can be achieved by selecting only a subset of columns in our experiments. Once you've finished analyzing your results, quit the result mode and don't forget to save the scene by clicking on the top left save icon. Let's proceed to create the second scene. Click on the Learning Module icon, then select the Create Scene button on the sidebar. Enter scene_2 as the scene name, and click on Create. As previously, a folder will be created containing models and notebook folders along with a .medml file. Double-click on the .medml file to open Scene 2. In this scene, we will compare model performance based on different data modalities. To do so, we will create 3 pipelines, one for studying the performance of a model using demographic and time series data, another using demographic and notes data, and the last one using demographic and image data. As explained earlier, we will use data only from the first 2 time points, assuming that models involving data from the last time points might make predictions too late in a patient's timeline. Let's begin with the first pipeline. Drag and drop a dataset node into the scene. Rename the dataset to DemTS for demographics and time series. In the File section, select T1_learning_modified and T2_learning_modified. In the Tag section, select TS Lab, TS Procedure, TS Chart, and Demographics. Then, in the Variables section, since the shown variables correspond to the selected tags, select all the variables. Verify that the target is set to target. Now, we are going to enable the same parameters as in the first scene. Click on the plus button and enable the index and session ID parameters. Then, enter subject_ID in the index section and 123 in the session ID section. Let's add another dataset node to the scene. Rename it DemNotes for demographic and notes data. Select T1_learning_modified and T2_learning_modified in the File section. In the Tag section, select In Radiology, In Discharge, and Demographics. In the Variables section, select all. Click on the plus button and enable the index and session ID parameters. Enter subject_ID as the index and 123 as the session ID. Finally, let's add our third dataset. Rename it DemIMG for demographics and image data. Select T1_learning_modified and T2_learning_modified in the Files section. Select Image and Demographics as tags and select all in the Variable section. As usual, enable the index and session ID parameters and set the index to subject_ID and the session ID to 123. Let's now add a Compare Models node to the scene. In the options, enable sorting and then enter AUC in the sort section. Here, we will return the best model considering the AUC metric for each pipeline. Let's finally add an Analyze node to the plot. Click on the node and press the plus button to show the options. Enable the plot option and then enter AUC in the plot section. Now, connect the 3 dataset nodes to the Compare Models node and connect the Compare Models node to the Analyze node to form the 3 pipelines. Run the experiment. If you take the time to observe the results, you'll notice that there doesn't seem to be a data modality that helps models perform better than the others. In the Compare Models section, the AUC scores of the best models from the 3 pipelines are very close. They are also similar to the results from the T1-T2 dataset in Scene 1, although none of them have a better AUC than in the first experiment with all the data modalities. Regarding the evaluation on the test set through the Analyze node, the model using Notes data performs poorly compared to the others, with an AUC of 0.53. The other models have approximately the same AUC on the test set as the T1-T2 dataset in Scene 1. At this step, don't forget to save your scene by clicking on the Save button at the top right corner. Well, in order to achieve the best possible results, we conducted experiments using combinations of data modalities, selecting only certain variables from all available options within each data modality, and testing various functionalities and parameters of the learning module. The experimentation conducted in the learning module mirrors what you will need to do in the final step of the testing phase. There will be a dedicated video on how to improve your experiments, so for this step 6, I will skip this part and simply provide you with the best pipeline that we found. Let's create this final pipeline. Start by adding a dataset node to the scene. Rename it AgeOPT, referring to demographic age variable and the optimal variables that we found. Select T1_learning_modified and T2_learning_modified in the File section. In the Tag section, select TS-Lab in Radiology, Image, and Demographics. In the Variables section, select the 13 variables shown in the video. Then, enable the index and session ID parameters and enter subject_ID as the index and 123 as the session ID parameter. Let's now add a clean node to the pipeline. This node provides a few options for data cleaning. Connect it to the dataset node. Click on the clean node and then on the plus button. Here, we enable 2 options: remove multicollinearity and transformation. Set these 2 options to true. Now, add a train model node and connect it to the clean node. This node takes 2 inputs, a dataset, which is the output of the clean node, and a model. So let's add a model node to the scene and connect it to the train model node. Then, in the drop-down selector of the node, change LR to ET, which stands for Extra Trees Classifier, the model we found to perform better on our data. The end of the pipeline will be separated into two parts, one to analyze the results of our model on the test set, and the other to finalize and save our model. Here, let's add an analyze node, as we did for all the other pipelines. Connect it to the train model node, which returns a trained model. Enable the plot option and enter AUC as the plot type. Now, let's add a finalize node to the scene and connect it to the train model node. This will allow us to train the model one more time, but this time on the entire dataset, both trained data and test data, without changing the model's parameters. Finally, add a save model node and connect it to the finalized node. This will allow you to save the finalized model in your model scene folder. Finally, run the experiment. If you open the results panel, you will see that 2 pipelines have been added for our new model. However, the results of the first 3 nodes are the same because these 2 pipelines share these nodes in common. The finalize and save model nodes don't return results. If you look at the results of the train models node, you can observe that the AUC metric is 0.70, which is better than all the other models tested in scenes 1 and 2. Then, if you look at the AUC plot from the analyze node, you can notice that the curves look good compared to the ones we obtained from our experiment, even if the score is not the best among the models we tested. The Save Model node is supposed to save your model in the Models folder of your Scene folder, so if you look into this folder, you should see the model, which is a .MEDModel file. As always, don't forget to save the scene. Otherwise, if you close the file, you will lose your pipelines. There are a few nodes that we haven't seen yet, such as the Load Model node. This node enables you to load a model saved as a .MEDModel file from your Models folder. There is also the Optimize node, which conceals a whole new set of nodes to optimize your models. If you want to learn more about it, you can check our GitBook. We will introduce it in more detail in Step 8 of this testing phase. Well, I hope you enjoyed working with the Learning module. In the next step, we will evaluate our model using the Evaluation module, and we will also utilize the Application module. See you there.